here we are in the Blanton Student Services Center, and one of the themes that we'll see in numerous places around campus is the architecture. There's a lot of beautiful architecture on the SMU campus, and so we'll look at the different mathematical things that architects do as they're designing a building. So one thing that we'll observe, and we see it very clearly here, is that architects will sometimes use a similar shape that will recur in multiple different elements of building as a way of tying together the different structures of the building. So look around at this space here and see if you see any particular shape that recurs multiple times in this space that we're surrounded by. Okay, as you looked around, you may have noticed a number of different things that occur. Obviously, there are rectangles and squares that occur multiple times. But a more unusual shape that you'll see multiple times in this space is a sort of oval shape. This particular oval is called an ellipse. And you will see it in this big gallery that I'm standing next to. You can see it in the molding here in the ceiling. You can see it on the floor of the space below me. There's a giant blue ellipse. And you can even see it in the arch that's right behind me. You see that element recurs. And so it gives a real unity to the design of this space. Now, to heighten that unity, it would be good if somehow the architect was using the same ellipse in each case. What do I mean by the same ellipse? Well, an ellipse is just a circle that's been stretched in one dimension. And that means that there are different kinds of ellipses. If we start with a circle, we could either stretch it a little bit to get an ellipse like that, or we could stretch it a whole lot to get an ellipse like that. Now, that means there are different kinds of ellipses depending on how much stretching. And what that stretching is a certain proportion between the shortest way across the ellipse and the longest way across the ellipse. So in order to check the ellipses that were used here in the Blanton Student Services building, we're going to want to actually measure those two, what are called axes of each ellipse. The minor axis is the short way across, and the major axis is the long way across. So we're going to measure the major and minor axes of a couple of these ellipses and see if we find a consistent proportion between those axes. The easiest one to measure is probably the arch behind me, so we're going to start right there. Okay, so we want to measure the major and minor axes of this arch right here. And we'll start with the major axis, which goes this way. And that's easy to measure because it's just the width of the entire arch. So we can measure that right along the floor here. And we'll just get the distance right across the arch. And it looks to be 82 inches. Okay, now to get the minor axis, it's just a little trickier because you see we really only have half of the ellipse here. So what I'm going to do is I'm going to measure the height to the bottom of that half ellipse, and I'm going to measure the height to the center of the ellipse, and then I'll take the difference, and then I'll double it because I have to imagine the other half of the ellipse under here. I'll start by measuring right along here, and it's a little tricky to know exactly where the ellipse starts, but there's a little clue in the seam of the woodwork right there. So we'll measure to that, and that is reading 81 inches. And now we need to measure to the center of the ellipse here, so we'll just lift the tape until it just touches dead center in the ellipse, and we'll read off. That's reading 106 inches. And so now if I take the difference, 106 minus 81, and then I have to double it because we only measured half the ellipse, that's a 50-inch minor axis. Now it's time to measure this big ellipse here in the center. And how are we going to do that? Because we can't stretch a tape measure across it. It would just slump and fall down into the space below. So we need to take advantage of some of the things in our surroundings and use a little bit of math to just even to measure this ellipse. So we look around at the space and ask, what could aid us in our measurement? And you may notice that the floor of this space, like in so many cases, has a nice square grid of tiling. And so we're going to use that square grid and a little graph paper to actually make a map of this ellipse. And we'll measure the ellipse on the map rather than measuring the real ellipse, because we'll easily be able to measure what's going on this paper here. Okay, so what I want to do is find the center point of the ellipse. That's right back here. And so this is going to be my starting point on my graph paper. And because I'm sort of thinking as I've started at the bottom of the page, and that direction is the top of the page, and I notice that the grid is arranged at 45 degrees to the axis of the ellipse. So I turn my paper at 45 degrees, and I pick any point down here, and that's my starting point. And I'm now going to keep the paper in this orientation. I'm going to keep facing that way, and I'm going to take a walk around the entire ellipse, recording what direction I go on the grid with every step. And I'm always going to try to stay as close to the ellipse as I can. So here's my starting point. I can't walk one square that way. I'd fall down to the floor below. So I have to step one step diagonally back into the right, and so that'll take me here. Now I can get a little bit closer to the ellipse, so I'll go here, and I'll record that on my graph paper. Now I can't keep going that way. I've got to step back, so I'll record that on. And now I can actually go 2 steps this way, and so I'll record that as 2 steps in that direction here. And now we're just going to keep doing this, taking steps and recording it on the graph paper. Now I'm all set. I can take 4 or 5 steps straight before I will have to turn to stay as close to the ellipse as possible. One more back here, and then one more this way, and in fact 2 more this way, and then 1 back here, and then 1 more this way, and then I go 1 back here, and now we've got a map of exactly half of the ellipse. Okay, and now I'm back around to where I've started, and I've got a complete map of the ellipse. And so this point that I marked where I started and the point where I marked where I was halfway around are on opposite sides of the ellipse across the minor axis. And similarly, where I was 1/4 of the way around and 3/4 of the way around are on opposite sides of the ellipse across the major axis. And so along here is the major axis. And along here is the minor axis. And I just need to now measure those lengths. So I need to know how big 1 square is. And you can measure the square with a type measure. It's also a very common standard size. These are 2-foot squares. So I know that the scale on my map is 1 square equals 2 feet. Okay, and now I want to measure these diagonals. And if you count, the minor axis is very close to 6 of the diagonal squares, and the major axis is 10 of the diagonal squares. And so I can now multiply by how long the diagonal of a 2-foot square is. We could use the Pythagorean theorem, or we could just multiply by square root of 2. And so we find out that the diagonal of a 2-foot square is about 2.8 feet. And I would multiply that to get these 2 dimensions. And now I want to take their ratio. So the ratio of the major axis to the minor axis, or actually it's easier to take the ratio of the minor axis to the major axis. And we don't even necessarily do the measurements. We can just take that ratio right here on the graph paper, and we'll get that it's 6 diagonal units to 10 diagonal units. So about 0.6 is that ratio. Now let's compare that to what we got on the in the archway. If you recall, we got 50 inches as the minor axis, over 81 inches was the major axis. And if I take that and I put it into my pocket calculator, so 50 over 81, and if I do that on the calculator, I get that it's about 0.617. So you see extremely close. We got 0.6 for the ratio for this ellipse, and we got 0.617 for the ratio of the arch. We see they're basically the same ellipse. And in fact, if you look at the places that we have on our map, they're the intersections of these grid lines. They're not quite exactly on the edge of the ellipse. If we actually measure those small distances from the grid lines to the ellipse and subtract those out from the 2 axes, you'll see that it actually even comes closer to the one on the arch. So they really are the same ellipse, and it shows how that uniformity of design from the architect helped to tie the architecture of this building together.